does that. And that's why the AC can enter ground, come out of the ground, and then complete with the transformer. Of course, it means your diode bridge, these points where you have ground here, have to all be connected. And that's how we get two diode drops from the D sub S to this point right here. Now there's also the version which is how does on the reverse current, AC basically has to come back to D3, and then now how does it get to this port, this terminal here?
31.
Yes, the only path is through D1, and the only path to D1 is through ground. So it passes through ground and returns to D1. So the bridge rectifier, how it actually operates. A ripple, let's say the capacitor here is 400 microfarad, the resistor is 450 ohms. Assume we're given these. So the question, find the peak-to-peak amplitude of the ripple. On the capacitor, sketch this voltage and mark its voltage and time parameters. So what type of rectifier is it? Is this full wave or half wave?
Full wave?
Is this full wave? Since it's a full wave rectifier, this is our ripple point. So we need the capacitor peak voltage. We need the capacitor peak voltage. And from our earlier calculation, from the transformer to this point here, the calculated capacitor is 21.3 volts peak. So we put that in the equation. What is this term T here?
Period.
Period. That's a period. So period is 1 over, we can actually give you, let's go back. The period frequency is 60 hertz, so it's 1 over 60 hertz. So divide that by 2 times 450 times 400 microfarad. The ripple is 983 millivolts. And where it says sketch this and mark its voltage on the time parameters, it's a crude sketch. That means draw a crude XY plot, and there are thousands of ways to draw it. Just draw something that looks like a positive DC. So that's showing peak to peak, and it says mark the voltage. So the peak here would be, if it's 983 millivolts, assume this is the peak. So that would be, you mark that 983, and this would be minus negative polarity of that. And then where it says mark the time, basically on this axis, this would be 1 over 60 here. And then you basically, that's probably enough for one, and then there's proof and put another on there. So that's what it means when you say sketch the ripple. And another question here, if the resistor is 300 ohms, whenever the load is equal to the maximum, the Zener current can fall to the minimum of 0.5 milliamp. So what's the maximum load current and what's the unit value of RL min? So what this question is asking is that our Zener, when the load current goes to maximum, this particular Zener will start to turn off. So it's asking what's the maximum, what's the smallest load resistance that we could use to keep the Zener in with the full reverse bias. So the way the question is stated, we have to meet VT0, we have R sub 0, I sub Z here is 1 milliamp. So VZ0 is 7.99 volts. And then this question here, capacitor minimum, we put all the numbers in here, we're calling it 300 ohm. The load maximum is 40.3 milliamperes, and then the load resistance itself with the Zener. This formula here is solving for I sub L max here. Oh, share.
Yeah. All right, guys. Okay.
Now, this type of problem, we're basically just kind of introducing it, and it's actually related. I'm going to jump ahead here. I don't actually have it on here. This is problem 6 on your homework assignment before it was actually removed. So this material was actually covering the material, what we needed in background for to complete problem 6. So what happened here is that problem 6 was removed from the homework, and at the same time, there really shouldn't be any questions like this on the midterm. These kind of get to be rather complicated questions. What we'll do in the course is later, after we cover MOSFETs, if we still have some time after that, we'll return to this subject. Now, it does mean that on the next part of the course is going to cover bipolar junction transistors and what else? What other devices? MOSFET transistors. So what this does, it leaves a window open that if we do have enough time later to return to this, then a simple question related to this type of design can appear on the final exam. So the final exam at this point can include a question about Zener diodes. Now I'll leave it for yourself to go through the math of these, of what's given in here. And there's some simple examples of Zener circuits here. This one, hypothetical, and this is fictional. It says peak frequency and amplitude are unknown, and there's a transformer. The ratio is 1 to 10. The Zener current is 10 milliamp. I sub Z is 10 ohms. I sub Z must never fall below IZ min of 5 milliamp. The load can draw 0 to 10 milliamp. The peak-to-peak ripple is 1.5 volts. The resistor is 300 ohm, and the load current is maximum. The minimum Zener current, which is all the way to IZ min, which is 5 milliamp. The capacitor is 100 microfarads. So we've covered everything to solve this problem. So to solve it, we take this equation, solve for VZ0, 7.9, and the question was asking what's the line regulation here. And then we'll study it. And then we come to find out that we're given R sub Z, and we're given the resistor 300 ohms. So all of this is responded to in this equation and this equation, and it's done. Now, this question was actually testing, do we really have a somewhat of an understanding of how we design a Zener? So this is a Zener that's already designed. And these two questions are saying what's the line regulation and what's the load regulation. You only needed two formulas to solve this problem. So it said we'll find out later if we can return to some of this material about the xenodiode. Now go for a moment here on the homework assignment in the low pass filter design and verification. It says the test in transient as demonstrated in example lecture notes. Let's find the point. The AC signal is 3.2 volt. The frequency is last numerical digit of the Z number. The noise is AC of 2 volt, 30 kilohertz. Use an op-amp low-pass filter. Choose the cutoff frequency slightly higher than the desired, 1.5 to 2 times larger, but sufficiently smaller than the noise frequency. You may have to experiment with a few choices. If you do, you just put your PSpice, your calculation for several what-if situations, and then in transient, you'll basically find out if your circuit is working. And then part D says calculate the attenuation of the noise, 30 kilohertz noise. Compare this with the 30 kilohertz revealed by your AC suite. How do you complete this part?
Find the amplitude of the signal at 30 kilohertz and then use the formula. You know? Or would you just, we have the formula for the gain at certain frequencies.
This page in the lecture notes. That's where it says calculate the attenuation of the 30 kilohertz. So make a note that it's asking you to use these equations to predict how PSpice will determine the output. The desired frequency is going to be the first calculation at the top. These are different frequencies and different cutoffs, but it's the same math. So at the desired frequency here at 100 hertz, the output is 0.95. You want that to be exactly 1, that's fine. 30 kilohertz gain is here. This equation is going to be 0.01. That's, what is that, minus 40 dB or so in PSpice. So that's what this is asking you to complete with this right here. Everyone keeping track of that. So I don't expect any open responses to that in the homework assignment because we basically pointed directly to it. So this is the paper calculation in that problem other than calculating your resistor and your capacitor. So it asks you to do something with this is a filter. It's not the exact filter that from your homework assignment, but it is a low pass filter. To complete that assignment, you'll need an AC simulation. So this is an example of an AC simulation of a low pass filter. AC swing. This is going from 10 to the 1 e to the 6 and 300 points per decade. here. Now, what mistake was made? Was the error just made?
This isn't not in decibels anymore?
It's not in decibels. And that's simple enough to repair here. You go and select dB, and then type V, V out.
Yeah.
V in is one, so we can, you can type it there or not. And then once you get your plot with your cutoff frequency, so this is one of the plots you'll need, and you'll go to plot and find the minus 3 dB. And we're somewhere down here. And that's approximately minus 3 dB right there. And we'll put it on your plot, make sure it's readable. So the minus 3 dB of this circuit is 496 hertz. And you can put it in kilohertz, and that's one of the plots you'll be needing. And since the cutoff here is, on this circuit, is 496, we'll assume we don't really have an idea what the cutoff should be, but let's assume it's around 30 kilohertz or so. So you'll take your, and you'll probably build a different schematic page. So the other plot it says to do is to plot this in, it's to plot this in transient. So to plot this in transient, of course you'll build a new schematic with the transient sources in it. Two sources, one for the desired and one for the interfering waveform. So we'll assume this, let's assume here, this says the desired is AC with amplitude of 3.2. And we're not really solving the problem, we're just kind of giving an idea of what it's asking. 3.2 volt. And the frequency is the last four of your Z number, so we'll, in order to pass through this low pass filter, the desired frequency we'll say is 100 hertz. We can make AC equal to 1. And we'll assume the interfere has an offset of 0. The amplitude is 30 kilohertz. And the amplitude is 2. Let's just make it 2. We'll make it the same as the desired. And then we'll make the frequency 30 kilohertz. centimeters depth. And now we've changed our simulation to transient. With time domain. And the desired, I mean,
It's at 20.
what's our runtime to capture 100 hertz for 5 cycles?
5 milliseconds. For 100.
You know, 100 hertz you want 5 cycles. What's our runtime?
20?
One over 100 times 5.
5.
5 milliseconds.
It's 50.
1 over 100 times 5?
These guys won't argue, so if it comes out too large or too small, we'll find out pretty quickly. Now since this is a, and we'll run the simulation again as a transient. And for transient, we do not use the DD. And we're getting some really strange output here. So what's going on with the circuit?
What is it?
What's the gain of this low pass filter?
The gain of this filter, which should be 1.
3.2K. 3.2K. So the gain is 1. The DC input is 3.2 volts. So 3.2 times 1 is a lot less than 12 volts. So it should not be in saturation. And then we can also, even though the output appears to be kind of unusual, the input also appears to be unusual. So what's going on here?
It seems, is it because a low pass filter has negative feedback, correct?
Yes.
Should there be a virtual ground effect at the pins 2 and 3?
It has a negative feedback to the converting input here.
So should the virtual ground effect be occurring here? No?
It should have, has 0 here and 19 microvolts here. That's pretty much.
But so it's effectively 0, correct? Is that what you should do? Okay.
The simulation is still time domain and to capture the 5 cycles of 100 hertz. 50 milliseconds should do that. But the question is, why doesn't it show the sinusoids at the input?
It's getting instantly filtered out because of how, because it's a linear combiner, right? Yeah. It's not linear combiner. I mean, no, the sources would just add up. So it's not interpreting it as, it's interpreting it as a bit more parts than it actually more parts. So. Ooh, okay. Yeah. So it was just instantly filtering it out to effectively, the gain was almost 0.
The filter now has only 100 hertz input,
Yeah, so
and on the plot on the output,
converting it.
V out and V in are the same, except inverted. Is this correct?
Yes, it is, because it's an inverting.
Why is it correct?
The op amp has a gain of -1, and it shouldn't be getting filtered at all at the
Well-
frequencies inside.
When we did the AC sweeping decibels, the cutoff of this filter is close to 500 hertz. So
Yes.
this is 100 hertz it's trying to pass through the filter.
So it passes
So
through.
100 hertz should have a gain of 1. So the input and output should be 1. If they are.
Yes.
They're the same. Now, we go back to the schematic, and we'll test the fear at the same time. Now, that's a lot of cycles for 30 kilohertz, so we'll leave it, find out what the simulator
So this
comes up.
was your-
And
Oh,
here,
that's
it basically is just too many cycles. So if we go back to our, and like 0.5 milliseconds. And then
Okay.
here, the traces are kind of uneven, so we can go in and try to make this 1 microsecond. And now, so this plot here, this is the input. That's the input, and this is the output. So is this correct? Is this what you expect?
Yes, what you expect.
At 30 kilohertz, the input is fine, 3.2 volts peak, and the output is a greatly reduced version of it here. So that question in the assignment is asking if your calculations are pretty correct. When you calculate the gain of 30 kilohertz, it's going to give a number here. So this says the gain is 0.01 at 30 kilohertz. So if the input is 3.2 volts, the output should be 0.01 times that. And you could put markers on here. You'd probably put this input on a different plot.
This frequency. This input frequency is like. Frequency.
So there's actually the output on a separate plot. So the filters, this filter is working properly. However, the assignment is expecting to put 2 of these in series. So now we'll make this one, this will be the desired of 100 hertz. And then we can make the other as is given. Now, because we're trying to capture the 100 hertz, let's make this 10 hertz.
increasing by few users.
This is an example of what's expected in the homework problem 3. It's showing, what is showing here?
The red would be the combined, the signal from the both VNs.
Okay, showing V in and V out. Here, V in. Which one is V in?
VN's the red.
The red. This is V in, it contains 100 hertz and the
30K.
30 kilohertz. That's why it has this kind of fuzzy on it. V out is only 100 hertz component. And it's approximately 3.2 of V in, because the 30 kilohertz is adding to the 100 hertz. V in peak to peak is different from V out. So this is something like your second one. And then
Did you enter like a 4D frequency?
what is that?
Did you enter a 4D frequency instead of 100?
Forward?
Like
No, this,
60,000?
your assignment will use the last 4 digits of your Z number in hertz.
No, I don't know what happened in my case. It's not doing the same
So
thing.
that, I just picked the cutoff here of, I picked it's an unknown cutoff. The cutoff here is around 500 hertz, based on as far as the time constant here. So the last 4 digits, I say yours starts with 8. That's 8,000. That's a large frequency to start with. 8,000 would be the desired, 8,000 something, and then the largest frequency, 999. The largest frequency, if all your numbers were 9s, the largest frequency would be 4 9s, and still, that's a lot less than 30 kilohertz. So your circuits
Indeed,
are
no,
still,
no, I'm not sure you will.
so this is what you should be getting with that. And now, once you get this, you have to come up with a creative way of explaining when you mathematically calculate it, why this filter should reduce to 30 kilohertz, do your numbers resemble what you're predicting in your paper analysis. It's really just a matter of doing a transient analysis and doing an ACDD analysis. The other parts, these are very straightforward diode simulations. You build a transient circuit. This is 1 kilohertz, and it's kind of detailed. There's 3-volt amplitude, and the frequency is 1 kilohertz, 1 to 3 milliseconds, and then show that the diode clips the start over here somewhere. Now, the decision you're going to have to make here is, how do we get this curve here? And it's saying show that it clips right here. So when you run this, it should clip around, instead of 3 volts here, it should clip around 0.7 volts. Is what it's doing. So your sine wave is going to clip at 0.7 volts. You're not going to get this drawing here. The only way to get this drawing is to do a DC sweep of the circuit. And the directions say instead of DC, use a sine wave. The next one, increased it to 8 volts. And even if you increase this to 8 volts, it's still, you get the same result, 0.7 clip. Reduce the amplitude to 100 millivolts, and now 100 millivolts is going to be below 0.7, so you won't get any clipping. Explanation, there's part of an explanation. If you rotate the diode 180 degrees, this is the new type of curve. Here is going to clip at minus version, it's going to be two diodes forward and backwards. So it's going to clip forward at 0.7 and then reverse at 0.7. So you're going to get a waveform, sine wave, that basically is clipped at plus and minus 0.7. This version, you put a battery instead of a 5 volt. The clip on the top is going to be 5.7. You notice the amplitude here is 5.7. And this version is two Zener diodes. They're 4.7 volt Zeners, so this will clip the sine wave at the Zener voltage, and then this will clip at the negative Zener voltage here. And then this filter, this is a half-wave rectifier. So if you take this circuit and then gradually, these are transient analysis for 60 hertz, and gradually increase the capacitor and resistor, change them, so that's 4 plots to do that. And that's a transient to show the filter. Another one, filter here, and then this problem doesn't really give the actual, just says it's a halfway rectifier, it's just saying how large should the resistor and capacity be to get an amplitude of 1.2 volts. We probably solved this one already in class already. And 5.3, another one, use a full wave rectifier, a bridge rectifier, and I think we just went over something very similar to this also. All right, our next session then is going to be our review, and we'll basically go over some types of problems, but it still says on your part, it's basically to prepare for the review, especially if you're going to have questions related to that. So we'll be here again on Tuesday.
And you said for the
On
midterm, it's gonna be
Wednesday.
5
What was that?
questions? You said it's gonna be